Good morning. Again, let me start off by thanking Professor Marek for inviting me. He's been telling me about this conference for many years, and for a variety of reasons, I was not able to be here, but I'm glad that I'm here this year. So again, pleasure, and I hope this is something that you're looking forward to. Let me talk a little bit about what advanced computing means to NASA. So I'm going to start off and kind of try to set the stage of where NASA comes from, what computing means to us as an agency, and then what are the things we are doing in order to not only advance the state of computing, but how computing can actually help a mission agency like NASA. So let me first start off by talking a little bit about NASA itself. Many of you probably don't know all the details about how NASA is organized, but I think this is somewhat important because that will put in context what we do in computing in order to advance NASA missions. So, I'm not going to read all of this here, but as you can see, NASA has a certain mission and a vision, but the idea is that to NASA, computing is an enabling technology. Unlike many other agencies, like the Department of Energy, for example, Paul is going to talk a little bit about that, or NSF, NASA's goal is not just to advance computing for computing's sake. It is about how computing can help what NASA's main missions are. And in order to understand that, NASA is organized in these 4 mission directorates. And so those are the primary focus areas for NASA. So of course, the first area is aeronautics. That's the first A in NASA. And the idea there is, how do we transform the entire aerospace industry? And that just does not mean building supersonic transport or reducing noise and emissions, better fuel efficiency, but also efficiencies and optimization in terminal areas, sequencing, and I'll talk a little bit about that. And that is the primary focus of the Aeronautics Research Mission Directorate. And obviously, computing plays a major role in order to enable and advance those objectives. The largest part of NASA is, of course, the Human Exploration and Operations Mission Directorate. And as the name implies, it is kind of focused on 2 primary areas. One is operations, so that is running the International Space Station. It's an international collaboration with many countries and many partners, with ESA and Jaxa and all of that. But also looking at exploration technologies that will take us to beyond low Earth orbit, to Moon and Mars and other asteroids and planets. And how are we going to be able to do that at low cost, being efficient, and that is where computing plays a major role. The other large part of NASA, of course, is the Science Mission Directorate, and that basically is broken up into 4 major areas. One, of course, is Earth Sciences. NASA, being a space agency, has a better perspective on Earth than all of the other ground-based agencies. Of course, we have NOAA, we have a lot of other agencies that are focused on Earth Sciences, but NASA, being a space agency, has a better perspective on Earth than anyone else. And so how do we enable that? But that's just only one part of it. The other major parts is heliophysics. At least in our solar system, the sun determines everything. So how do we understand space weather? What are the impacts of coronal mass ejections and all of that on life and communication, and the overall economy is a big part of NASA. And then, of course, we have planetary sciences and astrophysics. And then finally, the Space Mission Directorate is focused on technologies, all of the technologies that are required in order to enable all of these other various things that NASA intends to do. So again, the important thing to understand here is that to NASA, computing is a major enabling technology which drives everything else that we care about. So that's kind of one way of looking at NASA. Now, NASA is also a very large distributed federal agency. And as you know, you have the DOE labs and you have various universities doing things in support of NSF, in centers and all of that. NASA is also kind of similar in the sense that it's a distributed agency. Most of you probably don't know all of the centers, but some of the centers are very famous. Obviously people know Kennedy because that's where all the launches happen from. People know Johnson because that's where mission control is. But many of the other centers may not be that familiar. But within NASA, there are three main research centers, which are Langley, which is the oldest center, which was actually formed before NASA even came into existence, and that is focused on aeronautics. And then Ames Research Center, which was the second center that was formed because the United States decided that we needed a center as far away as possible from the East Coast. And so that's where Ames came in, and that was also formed before NASA was formed, because NASA was only formed in '58, but we are celebrating our 80th anniversary at Ames, so we were formed in '39. And then, of course, we have Glenn Research Center, which is focused on propulsion. Now, so obviously, I'm from Ames Research Center, and I believe that that's the best center among all the NASA centers. But more importantly, Ames being in Silicon Valley is in some sense, at the crossroads and the melting point of all innovation. And all of the things that we heard during Professor Pallis's talk about AI and Internet of Things and augmented reality and virtual reality and machine learning and quantum computing and neuromorphic computing and all of those things, there is someone doing something in the Bay Area. And so the way NASA also utilizes Ames Research Center is like a portal to the commercial sector and to industry, because as we all know, and I know that there are representatives or should have been representatives from the ministry, the government is actually not efficient in a lot of things, and we understand that. So NASA is also a government agency. And so what we try to do is but there are certain things that the government can do that no one else can do. So there are certain things that NASA is really focused on, and there are certain things that NASA believes that the commercial sector to do. And you've seen, and we'll talk a little bit about that in my talk, that is why we have these big partnerships with SpaceX and Boeing. We have the Commercial Crew and Cargo program. You probably have heard about DM-1, where SpaceX had the Dragon 2 capsule that is going to ultimately ferry crew to the station. All of that is part of NASA's goal to kind of offload some of the work that maybe SpaceX or Boeing or someone else can do better, and we should focus maybe on Mars and other more difficult destinations. So that is another thing we need to realize, that like the mission directors, NASA is also a distributed agency, and when we are trying to do these computing, we have to support all of these other things. So this is, as at least until tomorrow in the US, this is the current focus areas, because the budget is going to be rolled out tomorrow, the President's 20 budget. But until then, this is current NASA's focus areas. So the interesting thing is that of these 6 things, the word explore appears everywhere. And so that is NASA's main goal. And it comes in different flavors. Of course, explore flight. So almost every US airport and airline industry that uses something has NASA technology in there. And like I said earlier, NASA is always there with you when you fly, and so how do we make that better? Like the second area, the second picture on the top is the International Space Station. It's a major laboratory for the world. There are things that we can try out there. In fact, we had a collaboration with HP where we were trying to see if we can use software technologies to do radiation hardening. Because that's one of the challenges when we have with deep space missions, that computer chips and things that we use have to be radiation hardened, so there are several generations behind. And can you use software-enabled hardening to be able to recover from those faults? The third one, of course, is NASA's journey to Mars, and the moon is along the way, and how do we leverage living off low Earth orbit on the moon, and many of you may have heard about that there is a project to have this thing called the Gateway, which is like an orbiting platform like the station, but unlike the station, which is around the Earth, the Gateway is going to be around the moon, and so it will act as a waypoint to moon and to further distances in the solar system. The bottom row, like I said, the space technology and technology development is a major focus, And it's not about just doing technology development in-house, but technology that we are able to leverage of what is going on in industry and other places. And then also, how do we kind of do tech transfer? All of the things that NASA does, can there be a trickle-down effect where it helps in other, just commercial areas or in just the community that may have nothing to do with space? The fifth topic, of course, is Earth sciences, and we'll talk about that. And then finally, the last one is all about life sciences. Are we the only living organism out there? Are there things like us? Can it be anywhere? And many of you have heard about the Kepler project, which has identified many planets around other stars that are in this known as the Goldilocks zone, that they are just about the right distance from the star. They revolve or rotate at about the right speed. They have the right amount of gravity so that it has all the conditions, at least as far as we understand, to harbor and host life. I'm not going to spend too much on this, but this is just to bring back to NASA Ames Research Center. So the only reason for bringing this in is that several years ago, NASA decided that all of the computing is going to be consolidated at only one center, and that is at Ames Research Center. And because of that, all of the computing that is provided for the agency is at our center, but it also has the world's largest wind tunnel. As you can see, the test section is 120 feet by 80 feet. You can put a whole F-16 in there. You can put 18-wheelers in there. You can test out Mars parachutes. And we also have the United States, at least for NASA, the largest ArcJet facility, which when it runs uses up 120 megawatts of power, where you can actually test materials, both ablative and reusable materials, things that were used for the shuttle, and things that are going to be used for other vehicles, both NASA's and commercial or DoD. So digging down a little deeper, trying to look at what are the things that Ames is focused on, because we are a research center. So these are considered the 8 main core competencies for Ames. And I'll talk not all of them, but ones where computing plays a major role. And I'm going to come back to that a little bit later about what I mean by computing. But these are the main areas and you can almost imagine, even without me telling you, how computing can assist in each of these things. One, of course, is air traffic management. It's a scheduling problem. And if you throw in other things like weather and distributed control, it becomes a really, really difficult problem. And then if you now throw in that over the next few years, you're going to have drones and UAS in the system, how do you actually manage this entire air traffic system? Entry systems, which is this materials technology, both ablative and reusable, that's required for planetary reentry, not only of returning samples back to Earth, but it could be for sample returns from Mars, or also entering other planets that have some sort of an atmosphere. Advanced computing and IT, obviously, that's what I'm going to talk about mainly. But the other thing also is the intelligent adaptive systems. Autonomy is everywhere. We hear about self-driving cars, things that are autonomous. And especially for things that NASA is interested in, if you're going to do robotic missions, autonomy is a major part of that. So how do we do that? But another thing that we often forget when we talk about autonomy is the human autonomy teaming. If things were purely autonomous, then actually things might be easier because everything is autonomous. Things could go horribly wrong, but everything is autonomous. But it becomes really challenging when you mix autonomy and humans, because humans behave in unpredictable ways too. You can see this actually in Bay Area. If you go to Mountain View and you see a Google self-driving car, roaming around in the streets, people will cut in front of the car and jam on their brakes just to see what the Google car does. And so having humans in the mix makes things very unpredictable. It could be very useful. Obviously, there are certain things that humans can do better than anyone else. But when you have that mix, that's an important part to consider in how you're going to do autonomy. And even if we believe that eventually it'll be pure autonomy everywhere, there is still this transition period where we have to go through where we will have both autonomous things and humans playing in the same domain. The lower row, it talks about cost-effective or low-cost space missions. NASA's missions are extremely expensive. Many of them are over $1 billion. But the idea is that can you use small sats or nanosats and CubeSats? And you have heard about this. Ames was the one who kind of started all of these things, and now these have become very common. We have even university students working on small sats and CubeSats. But can you get, say, 80% of the science done for 20% of the cost? Obviously, it's not going to be as effective as a $1 billion mission, but for $200 million, can you get 80% of the science done? Can you also, using autonomy and other technologies, have constellation of satellites that together achieve a certain objective rather than a single mission like a Kepler or LADEE or L-Cross and things like that? So rather than having a single satellite that is supposed to do your mission, can you have several small satellites that work together to get the mission accomplished, even if one or more were to fail during the mission duration? Aerosciences, again, it's not only just the CFD part of it, but also how do you use wind tunnels and other test facilities in order to advance the state of the art in aeronautics. And then, of course, there's life sciences and earth science, and I'm not going to talk about them too much. So I wanted to throw this in because at the end of the day, what computations are trying to do is it's a sort of a digital transformation. And there are many ways of looking at it, but what we are basically talking about is you're employing these digital technologies, whether they're supercomputing, cloud, mobile computing, data analytics, machine learning, AI, all of that, to change a certain process, product, or capability so dramatically that the end result is undifferentiable from its original form. That, at least in our mind, a definition of digital transformation. So that means you need to do something such that, and it could be you change the product, the process, or the capability, so that the final thing looks exactly the same as it was originally supposed to be. And there are many examples of this, but this is a very small example, for example. So if you think about the entertainment industry, you have the traditional, you listen to the radio, and then of course you have CDs, and then you have, Spotify or, Pandora, things that are getting streamed to you. The same with navigation. You have paper maps, you fiddle around with it, then you have GPS that gives you a destination, and then you could have dynamic routing that actually tells you where to go and changes it. But all of and similarly in transportation. But in all of these things, the end product is undifferentiable from the original product, except that it's done differently. So when we talk about computing, and again, if you just focus on one of those things, how can computing do this enable this digital transformation so that you're able to do things more efficiently or better in some sense? Now, I probably don't have to convince this to everyone, but I think this is clear to at least everyone in this audience that, you could consider computing as digital experiments that are somewhat tradable with physical experiments. Almost everything that you do, everything that you can do digitally using a computer, you could do it physically also. And if you look at NASA specifically, the number of physical experiments that we did during the Apollo era and now is almost 3 orders of magnitude less. For every 1,000 flight tests or wind tunnel experiments that we did during Apollo, we are now doing 1. And so all that is replaced. Now, obviously, the risk has gone down significantly, but a lot of that has been replaced by digital experiments. Now, there are disadvantages of doing computer modeling. Your results are only as good as your models, and unless you actually bring in all the physics and the chemistry and the environment into your computer simulation, you're going to actually get bad results. But there are also certain things that you cannot do unless you have a computer. For example, you're not going to be able to see what are the effects of temperature rise or sea level rise because you're not going to be able to do that physical experiment. You're not going to raise the temperature by 2 degrees and see what happens. So there are certain things you have to do using a computer. So the fact that computing is absolutely necessary for the kinds of things that we do and interested in is kind of at least accepted and understood by this group here. So now let me talk a little bit about what we mean by computing. Generally speaking, computing is always considered to be supercomputing. When you normally talk about computing, people think, oh, we are talking about exascale and petaflops and HPC. But at least from a NASA perspective, computing in some sense, and I think this is now kind of also widely acknowledged, that computing is actually a much broader term. It could be obviously the massive supercomputing that we talk about, but it could also be these disruptive technologies like quantum and neuromorphic. It could be different delivery models like cloud, but also things like data-intensive computing and deep learning and machine learning and training. All of that could also be considered computing. Computing historically was you had a governing equation, you had a partial differential equation, you had turbulence model and things like that, and then you code it up and you run it on the computing, and that is what computing is. And that is still computing, but that, in my opinion, is just one aspect of what computing is. Computing is much broader than that. Where, if you talk about data-intensive computing, where you're ingesting large amounts of data and maybe you're just spitting out a very small answer, as opposed to CFD, where you're taking a structured mesh, you have the XYZ coordinates and the mesh is automatically generated, and you have some not simple, but you have some partial differential equations, and then you solve a time-dependent solution. So you have giant Q files with all kinds of velocities and temperatures and pressures, and then you solve that. So when we talk about computing, at least with NASA, we look at all of these things as being part of computing. So obviously, let me talk a little bit about supercomputing first. And from a NASA perspective, like I said, computing is all about enabling, and so we look at computing in 3 broad areas. One, of course, is what would be considered high throughput or capacity computing. I don't like to call it capacity computing in the sense that these could be independent calculations, for example. So suppose I'm trying to design this SLS, which is the Space Launch System, which is NASA's big rocket to take us to Mars and everywhere else, and you want to try to design the engine. So this is an engineering calculation. So I don't need thousands of cores. So each of these runs may only be 2,000 or 4,000 cores, but I may need to run 10,000 of those runs in order to finalize my design. So in some sense, it is capacity computing, and you could say that they are embarrassingly parallel in the sense that each computing is independent, each run is independent of the other run. However, it is a related run because I cannot make my final decision until I have all the runs in place. So therefore, if I just had a 2,000 or a 4,000 core system, I could still run these jobs, but it'll take me days to finish everything because I'd be running them one after another. On the other hand, if I had a large exascale, petaflop scale computing, then I can run many of these simultaneously and I get to an answer faster. So that is where, mission directors like Human Exploration and Operations and ARM and Space Technology, those are the mission directors that are focused on those kinds of calculations. But NASA also has a need for what would be considered leadership class capability computing, where I want to solve the largest possible problem that can fit on the machine. So it could be I want to do a global ocean simulation at 1/100th of a degree resolution. Or suppose I want to capture the vortex in an aeronautics field, in an aeronautics flow field with as many grid points I can possibly put in the vortex core. So those would be considered, capability computing, where we are trying to use the entire computer that I have in order to solve a single problem. But then we also have a need for high availability computing where, and this happened during the shuttle days when the shuttle is flying and I have some observational data that says that something may have been damaged during a launch. I have to run a simulation while the shuttle is on station so that I know that I can bring it back safely. And obviously, we missed some of these, and that is why we had those terrible disasters. But these are examples of high availability computing. I cannot have an experimental system which may or may not have a very high lin-pack number, but I must have the computer be able to solve the problem that I want done within a 24-hour or a 12-hour turnaround. And this is going to happen again when we have the gateway and SLS and all that when we are doing operations. So again, this is some numbers, and again, I don't want to dwell on this too much, but these are the kinds of systems that we have. The idea, of course, is that we need to have a variety of systems. It's not about a single system. So obviously we have Pleiades. This is a collaboration with SGI and now with HP, but we have other systems that have different kinds of Intel cores. They may be GPU enhanced because we are trying to solve some machine learning problems. We also have large shared memory systems because there are certain applications that might run on those. We also have a large visualization wall. Many of you who have visited Ames probably have seen it. This was the first, we were the first to kind of build this kind of a wall, and now those are available almost everywhere. But the idea is that you can use it to do computational steering in the sense that you can actually look at results while they are being computed. The reason that we have large number of small screens is because we are very interested in parameter studies when we are doing engineering calculations, as opposed to looking at a single large image. So we want to be able to see how, if multiple parameters are being varied, how does the results change depending on the values of those various orthogonal parameters. And then, of course, the storage and the networking and all of that. One of the things that has always been a challenge in computing is that you probably need a nuclear power plant next to your supercomputer in order to supply the electricity to the computing. And so one of the things that we have done recently is we are going into this more modular supercomputing facility. And again, this is a collaboration with HP. And the idea here is, and as I mentioned earlier, we are at Ames. We have in the Bay Area, the weather is almost perfect in some sense. So you can use a lot of the environment to actually cool your systems. And we have a lot of space also at Ames. So we are in the process of building this 1-acre site that will have 30 megawatts of power, can have up to 16 modules. Each module can have almost computing up to, easily up to 10 or 12 petaflops. And the idea is that not only does this allow us to take advantage of Bay Area weather, but also to be flexible, because each of the modules can have different configurations depending on the kind of things that we want, and also allows us to be, take advantage of the latest technology that comes out. So instead of having a single large system with the latest and greatest technology that is available here, we procure these systems over time so that so you're able to be agile so that you're always taking advantage of the latest technology that is available. Many of you may have seen this slide from my other talks, but one of the things that we always try to impress that if you have a lot of money, you can always go buy a big computer. That is not the problem. The problem is how do you actually use this computer to kind of solve the problems that you care about. And there have been many studies that have been done that shows that you have a big computer and you run lin-pack, and lin-pack runs at some 85% of peak, but then you're actually running real calculations. They don't run more than 10 or 12% of peak if you're running CFD calculations. And people have done all kinds of tricks. You can do lower precision arithmetic. You don't have to have double precision everywhere. You can do all kinds of accelerator technologies. But at the end of the day, to actually use computers, I don't know, but at least I do remember back in the day, you have these very fancy VCRs, and they all come with lots of things, but you don't know actually how to use it. So it's the same with many of these computers, is that they have a lot of peak performance and they have a lot of lin-pack performance, but it may not be able to solve the kind of problems that you care about at a large percentage of the peak. So this kind of shows the support that we also provide as part of a computing environment, is that it's not just, and if you go around the circle, if you look at the top, those are the various mission challenges, whether they be aeronautics or exploration or whatever that might be. But you provide the computational expertise to map those problems onto the hardware of the system, understanding what the memory sizes are, what are the cache lines, what are TLB misses, what kind of things that you can use on a attached a processor, that is an accelerator technology, all of that. You bring in the other modeling simulation aspects of it. You have the visualization, because that's an important part of very large calculations as well. You know, when you have petaflop scale computing, you're generating so much data that unless you have a very sophisticated way of looking at the output results, you're not going to be able to make any sense of all these results that your big computer is just spitting out. And then how do you feed all that back to the missions and to the customers and stakeholders in order to determine what's the next thing that you need to do. So since this is a NASA talk, there has to be some pretty pictures and animations and things like that. So let me talk a little bit about some of the things where computing is being used to do what we want. Now this is a very busy slide, but at least this is the big mission for SLS. So SLS is the Space Launch System. This is NASA's biggest rocket after Saturn V that took us to the moon. And the first mission is this thing called EM1. So EM1 is going to be an uncrewed mission. EM2 is going to be crewed, but EM1 is going to do a flyby of the moon. Okay, so it has various stages in there, and you can look at it. But the ultimate ideas are that there's a launch phase of it, then there is a return phase of it, and then there are, if you have crew, there are crew safety issues of that. So the first part of that is this whole launch environment. So this is actually a simulation of the entire launch environment. So there are two major aspects of launch. The first part is that how do you design the flame trench, that is at the top left corner, and understand how the plume actually goes through the flame trench so that it doesn't cause any sort of ignition overpressure, which is the kind of effect that happens during the first couple of seconds. So remember, once a rocket is supposed to be launched and is fired, it still takes about 2 seconds for it to clear the tower. And during that first 2 seconds is extremely crucial because of two things. You don't want to lose any stability or control on the rocket, because the rocket still hasn't left yet. It's just put out this huge thrust. And second, you also do not want to damage any of the payloads that you might have on the rocket itself. It could be humans, it could be biological samples, whatever that might be. And so as you can see, the entire CAD model is meshed up in a grid, and then you're doing that entire understanding the plume. And I don't know if you can see, but you can see the little green figures. Those are human-sized figures. So that gives you the scale of these calculations. So I think there are two. Obviously, those humans are not standing there at that time. But just to give you a sense of the scale, that shows you what is the size of this calculation. And as you can see from the upper left, the entire thing is modeled, meshed up, so that you are actually able to do this calculation. So the next stage of the rocket launch is after you get to a certain Mach number, so this is at Mach 4, the solid rocket boosters have to separate from the main core stage. And one of the biggest concerns is that you do not want it to come back and reconnect with the actual vehicle. So they should cleanly fall off. And so here's a simulation of the solid rocket booster separating from the core stage, and the plumes create some sort of effect on the rocket itself, and the number at the bottom left is the distance in feet from the tip of the solid rocket booster to the core stage. So you want that to be separating out nicely so that it doesn't come back and reconnect or retouch the core stage itself, and that there is no effect from those plume on the stability, because you don't want your rocket to suddenly be tumbling and all of that. So that's the second stage, which is after it has cleared, and then you have to get that out. But then there is a third important stage also. So there you have the rocket, but if I'm going to do a crewed mission, so then I have the multi-purpose crew vehicle, which is called Orion. And so Orion is sitting on top of this massive rocket with my 2 or 3 astronauts in there. And what if there is a problem? So then I have to have another rocket that is sitting on top of the crew module, which is called the launch abort system, that I have to now take the module off the rocket if there is a problem with the rocket. So I have a massive rocket, then I have two people sitting on top of it, but on top of those two people in the MPCV, I have to have another rocket so that I can take the MPCV off the rocket stack if this rocket stack now starts having a problem. And so we have to also have the launch abort system. And again, all of these are simulations that are being done. So I have to be able to take the Orion the crew vehicle off the rocket and then land it if there is a problem. And again, the idea of this is to take us beyond Earth orbit to the moon and to the gateway and to Mars and other places. And so here's a set of calculations, and again, I'm not going to go through all of these, but this shows all the various calculations that have to be done regarding the unsteady loads on that launch abort system, trying to understand the acoustics, because remember, I have humans in there that I have to save because my SLS blew up or something. And so these are massive simulations that are done on the supercomputers in order to be able to design, launch not only the launch abort vehicle, but also understanding what kind of pressures and G-forces and acoustics that might be created by this thing when you have a aborted system sitting below it, and then you have to take this off the stack. And then finally, related to this is, now if I have to land in these other planets or other heavenly bodies, I have to slow it down with these parachutes. And many of you have seen these parachutes when we had the 7 minutes of terror when NASA was landing Curiosity rover and all that on Mars. But you're not going to be able to test these kinds of vehicles, these kinds of parachutes, because you're talking about large payloads. So you have to land large payloads on the surface of Moon or Mars. So this is like a 60-foot wide parachute. And it's at supersonic speed. So this is running at, say, 3 Mach or something. So one, we have the largest wind tunnel. I can clearly test this, the parachute in my wind tunnel, because the wind tunnel is, like I said, 80 by 120 feet. But the wind tunnel is not supersonic or transonic. It's subsonic. So I'm not going to be able to test this there. Now, I have a supersonic wind tunnel where I can test out supersonic regimes, but that is only 9 feet by 7 feet, so I cannot fit this parachute there. So I have a couple of problems. I either have the size or I have the speed, but I don't have both. And so the idea here is, again, how do I do simulations in order to design these kinds of parachutes? What kind of spacing should I have in there so I am able to slow it down, but I don't want to tear this parachute also because I'm going to be, I'm coming in at, several 10,000 miles an hour speeds. So how do I do these models? So that's about exploration. Let me talk a little bit about other areas, because again, like I said, this is an area that touches almost everything. So the other part is aeronautics. So that was exploration. So let's talk about aeronautics. And in aeronautics, one of the major things is can we do commercial supersonic transport over land? We had the Concorde and we gave it away because it doesn't quite work. And the idea is, can I actually still do that and fly supersonic jets over land? And there are multiple facets of this that have to be solved. One, of course, is the jet noise. So this is an important calculation or aspect of noise that determines whether I can do those kinds of things. And again, this is where computers are playing a huge role in order to understand the vortical structure of these jet noises, what can be done in order to mitigate that, and to be able to capture these things at great detail. It provides the tools and the knowledge to the engineers to be able to design the next generation of, jet engines. Another major aspect of noise is the landing gear noise. In fact, that is considered one of the biggest problems of any airport, is when the landing gear is deployed, that creates a significant amount of noise that creates problems with communities living around airports. And so again, these are large calculations that are done specifically to understand the kind of noise and how do you mitigate that. And there have been a lot of things that have been done. For example, we have put in kind of like a toboggan kind of thing on the bottom of these landing gear in order to reduce the noise. But again, this is another big part of this. And then finally, we also do the incompressible flow inside the nozzles and the engines to understand what kind of noise is being created, and can we run, counterclockwise turbines to be able to get rid of some of those vortices or the noise. But again, these are kind of calculations that are being done in order to understand air traffic noise, engine noise. Now, as I said earlier, another big project that NASA has is this thing called urban air mobility. So obviously this is an artist's rendition, but the idea is that if you're going to have all these things flying around, and we just talked about engine noise and landing gear noise and fan noise, and now you have hundreds of these things buzzing around all over the time, it's going to be a nightmare situation to be able to take care of this. And so one of the things that we had done very early on is trying to understand rotor aerodynamics and aeroacoustics. So these are two calculations that were done a long time ago. This is several petabytes of data. But one of the problems with helicopters is that the vortices that get created by a leading blade actually is cut by the trailing blade that creates these vibration and noise. In fixed wing aircraft, we don't have this problem because these vortices that that come off the tip of these wings, they just go off into the far field, and unless there's another plane, tracking you very closely, it doesn't really matter. But in helicopters, the problem is it's your own blade that is cutting into your leading blade. And so those are two. One is in forward flight, the other is in hover. And this was a calculation that was done a couple of years ago to try to understand this very complicated vertical wake structure. And then we are using that, understanding that kind of research to understand. So now if you're going to do these quadcopters, and obviously we are doing lattice-Boltzmann calculations, we are looking at this Q criterion, which is a measure of the vorticity. And so here we are doing it on a Cartesian mesh with 11 levels of refinement. But if you're going to fly these quadcopters and octocopters all over the place, and you have Amazon delivering your books and McDonald's delivering your burgers and all that, and these things are flying all over the place, you have to understand all of these, not only from the noise characteristics, but its stability characteristics, but also you don't want these things falling off the sky because one of their blades broke. So how are you going to take care of all of these scenarios that are going to become, exponentially magnified when you have all these things flying around? So these are some of the calculations that we are doing in collaboration with many other partners, particularly Intel, to understand how can we understand the aerodynamics and this environment of urban air mobility. And then finally, at least as far as applications go, and talk a little bit about some of the large-scale calculations we have done. This was one of the largest calculations we had done. This is at 1/48th of a degree resolution of the entire ocean. And the idea is that historically we would do small regional simulations of that. But now you're able to do these global simulations, that the image on the left, but then you can take that down and do these downscale calculations and look at particular regions, whether it's the Gulf of Mexico or the tip of South America or some particular areas, whether around Japan. So you are able to do these kinds of things without inserting additional errors into your calculations because you're not making assumptions of the boundary conditions. You're able to use observational data sets to run or drive your entire global simulation, and then you use those to look at areas that and you can take it all the way down. You could just say, all I care about is growing wine in Napa Valley. I don't care about the rest of the world. All I want to know the conditions in Napa Valley so that I can grow grapes. And how do I do that if I can do these large simulations? So going beyond just large-scale simulations, I wanted to talk a little bit about other things that is held by computing. So this is one of the major projects within NASA, which is called ATD. This is the Airspace Technology Demonstrations. And like I said, it's not just about getting a good airplane or a quiet engine or flying at supersonic speeds, but it's also operations. So this is broken up into 3 projects. The first one was called ATD1, which is looking at how you can use machine learning and computational modeling to improve terminal sequencing and spacing. How can you get airplanes in and out as quickly as possible? And you want all the luggage to be moved from, it's an end-to-end mapping, and you have to get all the food in, you have to get all the passengers in and out, and you have to turn it around as quickly as possible. And so we did ATD1. We are now doing ATD2, which is not only looking at just the terminal sequencing, but now you're looking at schedule for gates and runways, and you want these long-distance airplanes that are coming in from San Francisco that are going to fly into Asia. Are they being treated differently from all these planes that are flying from San Francisco to LA, 5 times an hour? So how do you take care of that? And so that's the big ATD2 project, and that's a major collaboration with Charlotte Airport and American Airlines. And then we have ATD3, where we now take this and make it distributed, because now you want to execute more efficient flight paths, and you want to bring in weather and all of that, so that there is some distributed command and control, so that each aircraft is somehow making its own decision how it's supposed to do things, so that the overall thing is going to be efficient. And then, of course, later versions of this will bring in UAS and all that. We had also done this, just to give you an example of the kinds of things that we care about, we have also used computing to design buildings. And we don't care about buildings per se, but the idea was, can you do this to create sustainable habitats on Moon and Mars? So this was where we looked at computing to not only do the modeling of the airflow, and so this was the first LEED Platinum building in the entire US government, but then to look at how you can use control technology to be able to control, wastewater and electricity and opening and closing of windows and all of that. And so the concept here is, can you bring in all of the data sets to be able to design habitats that could stay elsewhere? Let me then talk a little bit about, data. So all we have done so far is we are generating large amounts of data and then we have to do something about it. So one of the biggest areas of NASA is Earth sciences data. Like I said earlier, we have large numbers of observational platforms, so we collect a lot of data. And how do we actually use that data to do something useful? So in Earth sciences, the biggest problem is that you have these Landsat images, you have MODIS data, and if you're anywhere in the world, you can log into NASA, you can send in a request for any data that you want. It is available to everyone. The only problem is you have to have storage on your side for me to send you the data. But any data you ask, I'll send it to you. The problem is what happens in Earth sciences is people from anywhere download these data, run some calculations, writes a paper, makes a prediction, and then what happens? Then the next person who comes in have no idea what this person did and is unable to kind of take that work forward. And so we created this thing called the NASA Earth Exchange, where it's kind of a social network, kind of virtual collaboration platform, where all of the data is in one place. People can use any of the modeling codes that they have, or they can put in there on the repository, or some that are freely or open source available. And then any of the data that is created, the derived data, is also stored in here, and then you can also capture the workflow. So then it allows a subsequent researcher to come and see what data was used, what was the codes that were used, what was the workflow that was used to generate the results, and then you can advance the state of the art. Because what we saw, there are a lot of time, and there is an OpenNEX version of it, which actually runs on the Amazon Web Services, and there is a portion of it that runs behind the firewall within NASA. Because a lot of this is not, ITAR data or classified data or anything of that matter, and many people will never have access to run on the NASA systems. But the data is freely available, and this is a good partnership with Amazon, where we are able to provide a platform to the community to be able to advance understanding of weather, climate, and all of that. And this is some calculations that were done. I don't want to spend time on this. But what this created is that we can now create these data portals, which is an idea of sharing and providing the ability to search large amounts of data that NASA has. So obviously, there is the NEX, which you just saw, and that is probably the most advanced of all the data portals that we have. But we also have a heliophysics portal. So there is like I said, heliophysics and how the sun affects almost everything that you do here. And so understanding those solar events and using observational, both ground-based and spacecraft data, and make it available to the heliophysics community is done through this portal, and it allows you to search things. But that has gone on to now we have this echo portal, which is that animation that you showed about the circulation and the climate of the ocean. And then we also now have a quantum portal where we are running quantum simulations, circuit simulations, that is now available to anyone. So you can actually go into any of these portals, and the websites are there, and you can go into any of these portals and get access to the data that we have, and you can search them. I'm not going to talk about this because I know right after this there is a lot of talk on machine learning and data sciences, but that is another, the only reason for showing this chart is that that is another big focus area for us, is like I said, not only looking at the data, understanding the data, and then doing deep learning, neural nets, and all of that on based of this data. So now let me talk briefly, I guess I have another 5-10 minutes or something, but let me briefly talk about some of the more disruptive technologies that are very important. So as you know, at least in computing, broadly, there are only 3 ways to do computing. One, of course, is your traditional computing, whether it be Intel processors, RISC processors, ARM, GPUs, I'm putting them all in the same class. Then, of course, you have quantum computing, which at least theoretically could change everything. And then you have neuromorphic. So quantum computing, I'm the overall lead for all of quantum computing for NASA, and NASA is doing this for a long time. Quantum computing is based on quantum mechanics. It is probably the most exotic field of all of science, and I don't want to spend any time explaining that, but there are certain features of quantum that are supposedly very promising that allows us to do certain things. And the idea is that, quantum mechanics deals with these phenomena that are at very small scale and at very small temperatures. And the idea is that there are certain effects at quantum levels, unlike classical, that allows you to do certain things. One, of course, is the fact that you have this superposition principle, that you can be in 2 states at the same time. Classical physics does not allow you to do that, but quantum mechanics tells you that you can be in 2 states at the same time. It also has this effect called quantum tunneling, which basically says that because of its wave-particle duality and all of that, you can actually go through a tunnel. You can tunnel through a barrier. Of course, these are special barriers, but you can tunnel through a barrier, whereas classical mechanics doesn't allow you to do that. And then, of course, there is this very exotic feature, which is entanglement, which says that 2 atoms are entangled so that each knows the state of the other instantly, independent of the distance that they're separated, and has nothing to do with the speed of light. Because in classical physics, of course, any 2 entities can know the state of the other as long as it depends on the speed of light, because that's the time it takes for that information to transmit. But in entanglement, in quantum mechanics, it doesn't require that. It immediately knows the state of the other atom. So the idea is, can you use these to solve certain problems that classical computers, traditional computers, will never be able to solve? Now, of course, the stories are never perfectly rosy. There's always a negative side to this. Because of its superposition and all of this, it has also this uncertainty principle. So that means if you solve anything on a quantum computer, it gives you a result, but you don't know whether that's the right result. So it's, in some sense, it's terrible because you spend all this time to solve the problem and you get an answer and you don't know whether the answer is right or wrong, because it always comes with a probability. And the only way you kind of mitigate these things, if you're trying to find an optimal answer, you run the problem many, many times and then see which answer comes out the most times, and you take that as an answer. But that's still a bad strategy, because you could take a US quarter, for example, and flip it 1,000,000 times and you get heads 1,000,000 times. Entirely possible, very unlikely, but it's possible. And you could perfectly conclude, therefore, that the US quarter has heads on both sides. because you just flipped it a million times. What you don't know, the next billion times it would have given you tails. You just stopped at a million times. So that's a problem. Or if you're trying to find an optimal answer, and you know that, let's say you know that the answer is 3, and you run this computer, a million times, and the shortest answer, the smallest answer it has ever given you is 4. It gives you a large number of answers, but it gives you a 4. And for example, a traveling salesman problem. If you're trying to solve the traveling salesman problem, there is one optimal answer, but every answer is a good answer, though. See, this is the trick of quantum computing, or when you're solving these NP-hard problems, is that any solution of a traveling salesman problem could be a valid solution. It's just not the optimal solution, but you don't know what the optimal solution is. But there are many ways of doing this, and then, the idea is that can you form this qubit? This is the special bit that has all these characteristics. You could do quantum annealing, you can use, quantum dots, you can use photons, you can use a bunch of things, but the idea is that you run this quantum computer in this entangled superposition state, but and so that means each of these qubits, so if you look at those, if you had 3 qubits, in a normal computer, you'd have these 8 states, but this has it has all those states, but are all superpositioned, except when you read it, it's going to give you one of those 8 states, but it'll give you a different state each time. The more important thing is, just to keep it with the theme of what I was talking about, is we NASA care more about what can these things do for us, is what can quantum computing do for NASA. That is the bigger question, rather than whether this device has entanglement or not is not my main concern. My main concern is, can this solve something that I cannot solve with my $200 million supercomputer? And so there are many examples of that. Data fusion is one. And you can almost think about these. If you think of an image, a particular image gives you a lot of information. But if you have multiple images of the same place, can you fuse those images to get more information than you could get from any one image? The problem is, if I have 1,000 images of the Gulf of Mexico, at different times of the day, different times of the season, at different frequencies, any one of those images have a wealth of information. But if I could merge, let's say 5 of those images, I could get more information. But which 5 of the 1,000 should I merge even? I don't know. And what am I looking for? I don't know that either. And so these are the kinds of things that quantum might be able to do. Of course, air traffic management, any time of scheduling or planning problem is an NP-hard problem, so you could solve that. And there's a variety of things on the right top. That's an actual signal from an instrument on the station. When things fail, there are certain signals. When hardware fails, there are certain signals that indicate that the hardware is going to fail. The idea is, can I track all these potential signals and trap them ahead of time so that I prevent it from getting to a point of no return? So I can actually stop it from being a catastrophic failure and return it back to normal operations. So that's one of the things that a quantum computer might be able to do. One of the things that we have been particularly focused on recently is quantum annealing, which is solving this, this Ising problem. And the idea is that, can you stay at the lowest energy state so that, and move adiabatically towards that lowest energy state while staying in that lowest energy state so that you can solve the problem. And this is very similar to simulated annealing, where in simulated annealing you use thermal fluctuations to get to the lowest state. And the idea is that this comes from metallurgy, for example, if you cool something very quickly, you will get your answer faster, but because you do it very quickly, you may not get the optimal answer. If you move it really, really slowly, you will probably get the ultimate answer, but then it'll take you forever to get to that ultimate answer. And so in quantum annealing, we are doing the same thing, but instead of using thermal fluctuations, you're using quantum fluctuations to get it to the lowest energy state. But again, these energy gaps are very tiny, and again, this is a whole talk on quantum computing, but these things are so tiny, so you do not want any excitation to move it up to a higher energy state so that you're no longer in the lowest energy state. So one of the things that we have been particularly focused on is this D-wave quantum annealing system. And the idea here is that it has these qubits that uses superconducting flux qubits to stay in this lowest energy state. And that's the whole system that we have. The largest system is at NASA Ames, which has 2,031 qubits, I believe. And what you can see there is at the bottom, at the extreme left, is an actual qubit. It's like it's a metal called niobium. If you make it into a ring and you cool it down to 20 millikelvin or below, it allows superconductivity. So electrons flow both in clockwise and anti-clockwise direction. And since it's a ring, and from college physics, you remember, so that means you're going to have both an up and down magnetic field through that ring. So that's your qubit. So that means that, so I now have a qubit which has both an up and a down magnetic field. So that means it's both in 0 and 1 at the same time. The problem is if I want to read that qubit, I have to send in a transverse signal that then forces it to either give it a 0 or a 1. And then those qubits are in a bipartite graph, which is the next figure. So each unit of D wave has 8 of these qubits in a bipartite graph. So there are 4 qubits, logically, that are connected to 4 other qubits. And then those unit cells are replicated in a chimera graph, which is the bottom right picture. And then each qubit then is connected to 6 other qubits. So each qubit is connected to 4 qubits within its own unit cells and to 2 other qubits in some other unit cell. And so that's your connectivity, and then you solve that problem. It only solves that one Ising problem, which is that summation over there to minimize it. And if it doesn't matter what problem you solve, you have to always get it down to that form. So here's a simple way of looking at how you're programming this system. You map your problem onto that cubo form, which is, it has to be of that form alpha Zij. But if it has more terms, then you have to do mathematical calculations to map it onto that cubo form. And then you embed that problem onto the hardware, which is the middle picture. And that's, I'm showing there 1 unit cell, which is the bipartite graph. And then it shows 4 unit cells, so you have to map it onto that. So you map the problem onto the cubo, then you embed it, and then you run the problem many, many times to get the answer that you want. I was not going to show this, but here just shows you how you actually solve the problem. So if you're trying to solve a graph coloring problem, this is how you actually take a problem and then map it to the cubo and then you solve it. As you can see right away that you're going to have all kinds of problems because you have this connectivity problem. So for example, if you want to solve that problem that is on the left, which is the original cubo, so that's the form you're trying to solve. You're trying to solve this problem J1, 2, x1, x2 plus J2, 3, x2, x3. So it's in the right form, so it's the cubo form. And you want to find the minimum value of HO. So that's your cubo. There is no way, there's absolutely no way to embed that onto the hardware. Because you don't have a hardware, because the hardware is right on the middle picture. There is no way to put that in there unless you have this ferromagnetic connection between 1A and 1B, because 1A and 1B are 2 qubits that are logically supposed to be the same qubit. Because you have to map that rightmost picture and the leftmost picture. They have to be the same. So therefore, if you're trying to solve that very simple problem, which is on the left, on the hardware that you have, that requires that those 2 qubits, 1A and 1B, have to be in lockstep. And so that means you're going to have a problem to solve that problem. And so if you can see right away, as the problems becomes more and more complex, you're going to have, and so for instance, the bottom right picture shows how different qubits in a hardware all have to have a ferromagnetic connection so that they're all in constant lockstep. And then the question becomes, well, which qubits are you going to make that behave like that? And again, here's some examples of the various things that we're doing. Complex planning and scheduling is one thing. We are looking at fault detection. So if you have a network, and I know my input conditions, and I know what my expected output condition is, and if it's a complex network, can I use a quantum computer to tell me the minimum number of faults in that system that would give me the wrong answer? So that instead, so because I have a complex network, so suppose and this is something that we are looking at also with Intel, where if I have an adder, I know that if I've given these bits, and I know this my answer is supposed to be, but I'm not getting that answer. But an adder may have many NOT and OR gates and all of that. So what is the minimum number of gates that could be faulty in order to give me the wrong answer? And then there's a whole bunch of other things that is also on the hardware side of it, because unlike traditional processors, classical processors, these things also have biases. So all the qubits are not exactly the same because it has all these physics involved. And so how do you actually correct those so that all the qubits behave exactly the same, which is another hard problem. I'm going to go past that and kind of finish with two small things. One, of course, is we have been talking about computing, quantum computing, but quantum could also be very useful for quantum communication. And so here's a project that we are looking at, which again ties back to urban air mobility. So what I want to do is, can I use quantum computing to assure robust communication? So for example, you can think of these really nightmare scenarios where you have a bunch of drones flying around, and can I drive an 18-wheeler with jamming technology along the highway that messes up all the communication among the drones so that they kind of fall from the sky or go off in wrong directions. So can I use quantum communication technology to assure that either jamming cannot be done, or I'm assuring communication between vehicles or satellites so that such things do not happen? And so here's a project that is going on where you're using quantum key distribution to spread the various spectrum codes, so that you're using quantum technologies, not computing, but just quantum technologies to address cybersecurity issues in urban air mobility. We are also looking at how you can use quantum technologies to connect space assets. So if you have a bunch of space assets, some of them are NASA assets, but some could be US or commercial or other federal agencies assets, and then you have different gateways on the ground, how can you use quantum technologies to be able to assure that you can connect securely, not only from a military or a DoD perspective, but also for assets that NASA has that prevents any sort of breaking into that communication links. And then finally, neuromorphic is another major area that we are also looking at. And I know that there's going to be talks about that. This was more about what neuromorphic computing is. I think there are other experts here who are going to talk about it. But let me talk just one slide on why it is important for NASA. So one of the things we want to use neuromorphic that I'm not going to be able to use a supercomputer on, because I'm not going to send a supercomputer to Mars. And I'm not sure exactly what I'm going to do with quantum computing, because quantum computing has all these promises, but it is so, let's say, flaky and not robust that I'm not sure I can use quantum computing to do certain things. But neuromorphic computing, I might be able to do a lot of things. So I can do a lot of in situ machine learning. They are much more robust. I can make them radiation hardened. I can put them on aircraft. I can put them on satellites. And the idea is that, can I use these neuromorphic computing chips, whether some of the things that IBM is interested in, some of the things that HP, or even there are small companies like Mentium that are looking at neuromorphic chips, that some of them are spiking neural networks, some of them are more of the traditional neural networks. We are working with Intel on their Loihi chip to try to understand how it can be used. But from our perspective, can I embed these neuromorphic chips on my assets to be able to do in situ detection and learning? So again, that brings me to my last slide. Again, reiterating once again that at the end of the day, from NASA's perspective, the idea for computing is a very broad area. And the idea is that, I'm done actually, this is my last slide. Can I enable science and engineering for NASA's missions and goals? And these are all over the place. Like I said, this is Kepler, which is looking for Earth-like planets around some other stars in distant galaxies, to real-time prediction of hurricanes and tornadoes and all of that, to Launch Complex, Earth Sciences, rotorcraft, quadcopters, UAM, understanding how the universe was formed, merging of black holes and all of that. I didn't talk about that. And then also engineering things that NASA cares about, like Space Launch System and Orion. So with that, I'm going to stop here, and I'd be happy to take whatever time we have for questions. And then, of course, I'm here. That's it. Thanks a lot.
Now we have about 10 minutes for questions. If you have any questions to our speaker, please.
Hello, thank you for your very informative presentation, very beautiful spacecraft launch simulation. I have a question. You said you need to process very big tasks on very big grids, and how do you make it possible? Do you just use more and more main memory, or do you apply some special localization algorithms?
Yeah, so yeah, it's a combination of all of that. So it could be a variety of things. So, you know, one of the things that many people sometimes forget is that just because you have a large computer doesn't necessarily mean I can run a larger calculation. I cannot just throw in more grids, more grid points. So for instance, suppose I have a exaflop computer as opposed to my petascale computer, so now I have 1,000 times bigger computer, and now I want to do a more finer resolution of the global ocean modeling. You just cannot do that, because then your physics is incorrect. Because once you start making your grids finer and finer, you have to also consider that the ocean is no longer a homogeneous fluid anymore. So when you are doing an ocean simulation and your grid points are, let's say, 1 kilometer apart, and you want to go to half a kilometer, that might be okay. But now if you have a big computer, and now you can make a grid that is 10 meters, well, now you have to model all the whales and dolphins in the ocean, otherwise your calculation is wrong. So that is one important part. So just because you have a bigger computer doesn't mean you can just increase the grid points or the resolution without taking into consideration what the problem you're trying to solve. And then second part of it is exactly what you said. You know, you could have different algorithms that you may want to look at. There are many algorithms, you know, there are dense linear solvers, you know, there are iterative methods, you could do all kinds of, you know, Cholesky decomposition and all of that. But the question is, at the end of the day, you also have to see what your computer is able to do. Many things that we have done over the years in terms of, say, adaptive grid computations or, you know, higher order methods may be theoretically, when you do an analysis, might say, oh, this method is better than that method. But on a certain computer, the reverse might be true. You know, memory might be so cheap that you don't have to fool around doing all of that thing. You can probably do a direct method as opposed to an iterative method. It's possible. The other thing also is, the third aspect I would say is that you also need to look at whether you should use accelerator technologies, whether it be GPUs or whatever it might be. So I'm saying at the end of the day, it's a combination of three things. You just cannot solve a larger problem just because you have a greater supercomputer. You have to make sure that you have your models right, otherwise you're just producing garbage at a faster rate. The second thing is you have to look at the algorithms and numerical algorithms and all that actually fits better with your problem, not necessarily a theoretical work that says certain algorithms are more efficient than others. And then finally, I think it's not just using brute force method. You have to just look at combinations of hardware as to what might help. Any other questions?
Hello, thank you for a great talk. Paweł Goła from University of Warsaw. I have a question about quantum computers which you use at NASA. So have you achieved quantum supremacy in any of problems which you try to solve? I mean, or are there any chances to get better results or speed up in any of real problems which you try to solve using quantum computers?
Okay. So let me just first of all say that I am personally not a big fan of this word quantum supremacy. I know that's a word that is used everywhere. I kind of feel that it's a little tacky by saying that we are more supreme than everyone else, but I think I would rather like to use the word like a quantum advantage rather than supremacy. So there are a couple of things that have happened. One is a paper that had come out between NASA and Google several years ago where we compared a particular application that has a certain characteristic, because you remember the one advantage of quantum computing is that it has this tunneling property. But the tunneling only works for certain barriers. So if you come up with a certain application that has these really thin barriers but are deep, that's where classical, so before I start there, one thing you have to remember that if your barriers are very short and fat, classical computing is not going to be able to help. Quantum computing is not going to be able to help, because quantum computing is not going to be able to tunnel through short, fat barriers. So classical computer will be as good or as bad as quantum computing. But quantum computing can win if you have these thin barriers that are really deep, because then classical will get stuck, but quantum will be able to tunnel. So we had done a paper 2-3 years ago with Google where we showed that a quantum computer could be 9 orders of magnitude faster than an Intel core. But that was not quantum supremacy. So one of the things that we are looking at is, many of you know Google has this chip called Bristlecone, and this is this universal quantum chip that we are working very closely with them. And what I talked about is what we have now done is we have done the circuit simulation for that chip on the Pleiades supercomputer, which is the NASA supercomputer, up to 70 qubits. And that runs, so that allows us to show that if that Bristlecone chip were to be done at least 45 or 46 qubits, then that will achieve what is known as quantum supremacy. So half of the problem is done in the sense that we now have this circuit simulated on the machine up to 70 qubits and shows quantum supremacy, but only in simulation. Google still has to build this Bristlecone chip, which I think is currently at, 30, 40 qubits or something, but at least has to be at 45 qubits to be able to do that. We are running the simulation also on the Oak Ridge Summit machine, and we are going to run it also on the GPU, on the TPUs that Google has, and we ran it already on the NASA supercomputers. So we expect that quantum supremacy thing to be achieved sometime over the next 2-3 months. But we are waiting for Bristlecone to be ready. I have a question there.
Bogdan Lessing, Faculty of Physics, University of Warsaw. Supercomputing simulations are capable to really precisely predict evolution in time complex systems. So we can predict how systems evolve in time, but in many cases we do not understand why some events occur or why some events happen in such evolution. So the question is, do you develop or apply causality analysis for post-processing of complex supercomputing simulations?
Yeah, that's a kind of an open question. That, it depends on what, maybe we should talk a little bit more so that I understand this question better. But I think one of the things that we do, for example, when we are trying to solve CFD problems, all we are saying is, okay, I have a bunch of governing equations, Navier-Stokes, Euler, whatever, with variety of turbulence models, and I'm going to solve it and see. So there is no causality of that. As long as I trust my governing equations, it gives me something. The thing that we do in earth sciences, for example, is what is known as data assimilation. So suppose I model the entire global oceans or the atmospheric model, and then I make a prediction that 20 years from now, it's going to be 2 degrees warmer or whatever it is, or sea levels will rise 10 meters. But for those kinds of things, the most important thing is to actually run the model backwards, take observational data sets from 50 years ago, run your problem with the data set that you had at 50 years ago and run it to the present, and then you see, does your model give you the same answer that I can observe now? Making a prediction 20 years from now doesn't help unless I can see whether the model, so now I wouldn't call that causality, but at least that is showing some sort of my confidence in my model, that if I ran it something. Now, there could be other things. For example, we also run this cosmology simulations where we start from the Big Bang and we run 13 billion years into the present and say, okay, if we had this original filament structure and if these things just by gravity evolves, and I run this simulation 13 billion years into the future, come to the present, and then I observe, am I getting the same thing? I don't know whether these would be called causality, but I think there are, I think these are two kinds of things that we're doing. One is running things from the past to the present to see whether it matches. and then running things from the present into the future and making predictions. So I don't know if that quite answers your question, but maybe some hand-waving answer to your question, I don't know. Any other questions? Okay, we have gotten the signal that it needs to end right now. Again, thank you very much for your attention, and Marek, pleasure being here.